We constructed the most sophisticated optical instrument humanity has ever created. Decades of collaboration, billions in funding, the brightest minds across continents working toward a single goal, confirm our theories about the cosmos. Instead, it became something far stranger, a mirror that reflects not confirmation, but contradiction. A window that reveals not answers, but deeper questions that shatter our foundations. This is the story of how scientific certainty crumbled, and why a Nobel laureate's heretical theory is beginning to look prophetic. The tension is real. That is the most unsettling conclusion modern cosmology has reached. When scientists measure how fast the universe expands using observations from the earliest moments, they get one number. When they measure the same expansion rate in our current cosmic neighborhood, they get a different number. The discrepancy reaches 9%. In the precision-obsessed world of physics, this is not a small error. This is a chasm. This is evidence that something fundamental is broken in our understanding of reality itself. The universe, it appears, is not behaving according to the script we wrote for it. For decades, we had a story. It was elegant, mathematically beautiful, and it explained almost everything we could observe. The narrative went like this. In the beginning, approximately 13.8 billion years ago, existence emerged from an infinitely dense point. Time and space themselves were born in that moment. Reality expanded from that seed, cooling and spreading, becoming increasingly complex. From primordial hydrogen and helium, the first stars ignited. These stars formed the first galaxies. Galaxies clustered together. The universe evolved according to laws we could write as equations. When we looked at the ancient light still traveling toward us from that early era, the cosmic microwave background radiation, it confirmed our story. We saw the fingerprints of a universe following our predictions. We were right. Or so we thought. The hairline fractures had been forming quietly. Observations here and there that didn't quite fit. Nothing dramatic. Nothing that would immediately overturn the established model. But they accumulated, spreading slowly through the edifice of cosmology like cracks through ancient stone. Where would these cracks lead? What lay beneath the surface of our confident pronouncements? Then, in the span of just a few years, everything changed. There exists a physicist whose contributions to science are so profound that they earned him the highest honor the scientific community can bestow. Sir Roger Penrose. The year was 2020 when he received the Nobel Prize in Physics, but the award recognized only one aspect of his genius. Decades earlier, he had proven something that still shapes how we understand black holes. Using nothing but Einstein's General Relativity, without invoking exotic new physics or speculative theories, Penrose demonstrated that collapse to singularities was not merely possible, it was inevitable. Under normal astrophysical conditions, the fabric of space and time must break down, must reach points where the equations of physics lose all meaning. This alone would have secured his place among the greatest minds in science. But Penrose did not stop there. He spent years contemplating these singularities, these boundaries, where physics ceases to function. He questioned their nature with the intensity of someone wrestling with the deepest riddles of existence. Out of this meditation, he developed a conception of the universe so radical, so challenging to conventional wisdom, that even his peers found it difficult to take seriously. He called it conformal cyclic cosmology. The idea can be stated simply, almost deceptively so. The universe has no beginning. It has no end. Instead, it progresses through phases, each one called an eon. Each eon commences with something resembling a big bang. Indescribably hot, impossibly dense. The universe then expands, cools, empties over spans of time so vast they exceed our linguistic capabilities. Over intervals of 10 to the power of 100 years. Over Google years. Everything that once populated the cosmos transforms into a thin dispersal of massless particles. Photons. ghostly radiation drifting through an increasingly empty expanse. And then something remarkable occurs. In this state of ultimate expansion and depletion, when the universe has become nearly void, mathematics reveals something astonishing. The distant future of one eon becomes geometrically identical to the inception of the next. The mathematics is not approximate, it is exact. The end of one cycle becomes the beginning of another. Death transitions into birth. Birth emerges from death. Continuous, seamless. No singularity where physics breaks apart. No moment where the equations become meaningless. How could such a transformation be possible? The answer lies in something called conformal geometry. This branch of mathematics studies a special category of transformations. These transformations can stretch or compress space and time dramatically. They can alter scales completely, yet they preserve certain fundamental relationships. The angles between curves remain unchanged. The shapes stay intact even as their sizes are transformed beyond recognition. Penrose recognized something profound about the nature of particles at these extreme densities. Photons, those packets of light, are fundamental to the universe at these scales. A photon does not experience the flow of time. From the perspective of relativistic physics, there is no past or future for a photon. There is no duration. The photon's emission and absorption happen simultaneously, separated by no time at all, regardless of the distance between those events. Billions of light-years mean nothing to a photon. They occupy the same instant. If the universe becomes composed entirely of such particles, scale becomes meaningless. There is no instrument to measure distance, no clock to measure duration, no ruler to establish size. In a universe made purely of particles that experience no time, the concept of scale vanishes. And when scale vanishes, the conformal transformation becomes possible. The infinitely expanded, empty final state of one eon becomes indistinguishable from the compressed, dense beginning of the next. Not metaphorically, mathematically, precisely. But mathematics alone does not make a theory true. Science is littered with beautiful equations that describe no reality. What transforms Penrose's mathematical elegance into a scientific hypothesis is the question of testability. If this theory is correct, if universes truly cycle through these eons, what observable evidence should remain? What fingerprints would a previous universe leave upon our own? Penrose's answer was bold. Look at the cosmic microwave background radiation. This is the oldest light accessible to our telescopes. It was released approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to form stable atoms. At that cosmic moment, the universe transformed from an opaque soup to something transparent. Light, previously trapped and scattered, could finally propagate. That light has been traveling toward us ever since, its wavelength stretched by the expansion of space, its energy shifted toward longer wavelengths, its colors reddened. It reaches us today as microwave radiation, an ancient signal, a message from cosmic infancy. Within this radiation, Penrose proposed, would be signals from before our Big Bang, concentric rings, circular patterns in temperature variations, evidence of supermassive black holes from the previous eon evaporating through the process Stephen Hawking described decades earlier. At the boundaries of black holes, quantum effects cause particle-antiparticle pairs to form. Occasionally one falls inward while the other escapes. This represents an energy loss for the black hole. Over time, the hole evaporates. For supermassive black holes, this process takes incomprehensible durations, 10 to the power of 100 years, far longer than the current age of our universe. But in the dying universe before ours, there was infinite time. All the supermassive black holes evaporated. Their final radiation would transfer to the next aeon through the conformal transition, appearing to us as heat signatures in the cosmic background. When Penrose and his colleagues published their analysis in 2010, they reported finding these structures, concentric rings in the temperature data, patterns too statistically significant to be random noise. The probability of their occurrence by chance was less than 1 in 125. The scientific community reacted with skepticism. Other researchers generated simulated maps of the cosmic background based on the Standard Model, based on no exotic physics, no traces of previous universes. They found just as many rings. The phenomenon known as the look elsewhere effect explains this easily. Search through sufficient amounts of random data, look in enough different places, and you will inevitably find patterns that appear meaningful even when the underlying data contains no real structure. It is statistical illusion. Penrose countered, insisting the analysis was sound. The debate raged in journals, at conferences, in public forums. Then it faded. Not resolved, not definitively disproven, simply abandoned to the margins of cosmology. An intriguing but probably mistaken idea from a brilliant mind. Most cosmologists dismissed the entire endeavor, Penrose continued. He did not relent. But while theorists debated on paper, something concrete was missing. All these ideas about cyclic universes and ghostly echoes, no matter how mathematically sophisticated, remained hypotheses. For science to advance, observation was required. A new instrument capable of seeing the universe in ways previously impossible. A new eye that could test these competing theories. Then, on December 21, 2021, on Christmas morning, humanity launched such an instrument. The James Webb Space Telescope was not simply a larger Hubble. It represented a qualitative leap. Its primary mirror spanned 6.5 meters. It consisted of 18 hexagonal segments coated in gold, designed to fold together for launch and then unfold in space like the petals of some mechanical flower. Webb could perceive wavelengths far beyond what human eyes could sense. Infrared light, the longer wavelengths that redshifted radiation becomes when stretched by the expanding universe. This capability was crucial. To see further back in time means seeing more redshift. To see more redshift requires sensitivity to infrared. Webb could observe distances where Hubble went blind. It could examine the first galaxies that ignited after the Big Bang. It could study epochs when the universe remained young, turbulent, hot, the seedbed of all modern structures. In July of 2022, Webb began its scientific observations. Almost immediately, the universe began asking questions that shattered conventional answers. The first findings were seismic. Across the scientific community, shock waves propagated. The term that emerged was striking, almost accusatory in its audacity. Universe-breaking galaxies. 6 of them. Observed when the universe had not yet existed for 500 million years. On the cosmic calendar, this was a fetus attempting to complete a marathon. Impossible. According to the Lambda-CDM model that had dominated cosmology, galaxy formation proceeds patiently. Gravity pulls together small concentrations of dark matter. Gas cascades into these wells, stars ignite gradually. The process spans billions of years, a construction project of immense patience, slow, methodical. Yet Webb revealed something that violated every expectation. These galaxies emerged as titans. They possessed masses 10, 20, even 100 times greater than models predicted possible for that age. The data was unambiguous. These were not measurement errors. These were not observational illusions created by dust or distance. The photons collected by 18 gilded mirror segments told an unambiguous story. These galaxies were not only massive, they displayed maturity. Sophisticated structure, complex chemical composition. Forms that should have required billions of years to develop. Yet they existed when the universe was still an infant. Scientists reacted with disbelief. Surely instruments had misread. Surely something was distorting the observations. Analysis was repeated. Results were confirmed. These galaxies were real, and with their confirmation, The elegant structure that cosmology had built over decades trembled. Not collapsed, not yet, but trembled. Then chemistry itself became impossible. A galaxy designated by astronomers as Sears 93316, nicknamed Maisie's Galaxy. When Webb's observations captured its light, the universe possessed an age of 390 million years, the cosmic dawn. Yet within this galaxy, Webb detected something that absolutely should not exist. Oxygen. This element is not simple. It is not primordial. Oxygen forms only in the cores of stars. In the nuclear furnaces where helium transmutes into carbon, then carbon into oxygen. For oxygen to accumulate in a galaxy requires an elaborate chain of events. A star must form. It must burn for millions of years. Then it must detonate as a supernova, scattering oxygen into space. This oxygen-enriched material must cool. It must condense into a new cloud. New stars must form from this cloud. This cycle must repeat many times, accumulating oxygen layer upon layer. According to stellar physics, this process requires a minimum of 500 million years. More realistically, a billion years. Possibly longer. Yet Maisie's galaxy, at 390 million years, contained spectroscopically verified oxygen. The timeline had become impossible. Something that requires 500 million years of stellar processes existed in a universe scarcely older. This was more than an anomaly. This was violence against the fundamentals of stellar evolution, against our deepest understanding of element formation. And Webb discovered this was not isolated. Everywhere it examined the early universe, wherever it turned its attention toward galaxies in cosmic infancy, it found carbon, nitrogen, oxygen, elements forged in stars, elements that should require countless generations of stellar birth and death, yet they suffused the early universe. The cosmos appeared chemically ancient when it should have been chemically newborn, as if someone had administered stimulants to every runner before the race began. But the strangeness continued escalating. As Webb conducted its deepest observations, peering into the most remote regions of space and the most ancient epochs of time, it encountered hundreds of previously unknown objects. Compact, intensely red in their appearance, mysterious. No one had predicted their existence. No model accounted for them. They appeared within the first 500 to 700 million years of cosmic history. Initially, their nature remained uncertain. Speculation abounded. Then, in 2024, researchers from the University of Copenhagen presented their analysis. The revelation was shocking. These were not galaxies. These were black holes. Young black holes, actively consuming material from their surroundings. But what black holes they were! The smallest among them possessed masses equivalent to 10 million suns. Some were larger still. Stop and consider this. 10 million solar masses. The universe not yet a billion years old. By definition, physical impossibility. According to standard black hole physics, a black hole begins its existence from stellar death. A massive star collapses. The resulting object weighs perhaps 10 to 100 times the sun's mass. It then grows by absorbing surrounding material and by merging with other black holes. But this growth has a speed limit, the Eddington limit. If material falls inward too rapidly, the resulting radiation pressure prevents additional material from falling. The black hole strangles its own feeding mechanism. It cannot exceed a certain accretion rate. Under this constraint, developing a 10 million solar mass black hole would require hundreds of millions of years, perhaps billions, perhaps far longer. Yet these monsters existed when the universe measured only a few 100 million years old. The equation of time had collapsed. Either these black holes grew far faster than physics allows, or they did not begin small. They did not grow from stellar remnants. They arose from something else entirely. This discovery catapulted theories that had dwelled in speculative obscurity into mainstream scientific debate. Direct collapse models, Primordial black holes, radical mechanisms for generating massive black hole seeds without relying on stellar deaths. The Standard Model had no framework for explaining these observations. The scientific community faced a choice. Either our most fundamental understanding of how black holes form requires complete revision, or the universe itself operated according to different rules in its infancy. But the most destabilizing discovery concerned something deeper than any individual object. It concerned the nature of the universe itself. JWST 130. Commit this name to memory. It is one of the most distant, most ancient galaxies human instruments have ever observed. When Webb collected its light, that light had traversed 13 billion years of expanding space. The universe was merely 330 million years old when this light was emitted. Barely a newborn. At that epoch, the universe was supposed to exist in a specific state. It was supposed to be shrouded in dense fog. Neutral hydrogen atoms filled all available space. A cosmic dark age. This fog possessed the ability to absorb certain wavelengths of light, particularly a specific type called Lyman alpha emission. Seeing such emission from a galaxy of that era was not merely unexpected, it was supposed to be impossible. The fog would block the signal. Like attempting to perceive a lighthouse from miles away through heavy mist, the light would be absorbed, the signal would be lost. But Webb detected the Lyman alpha emission from JWST 130, clear, bright, undeniable. The universe's cosmic fog had not blocked it. There was only one explanation. This single galaxy had accomplished something extraordinary. It had punched through the surrounding cosmic fog. More than that, it had created a massive bubble of ionized gas around itself. An oasis of transparency, a region of ionized hydrogen 650,000 light-years in diameter. This remains the largest ionized region ever observed at such an early epoch. To grasp the magnitude, consider this. The galaxy itself possesses width perhaps 10,000 light-years across, yet it had ionized a region more than 60 times larger. A single 330-million-year-old galaxy, clearing an area thousands of times more vast than itself. What energy source could accomplish such a feat? What mechanism could generate the power required? Either this galaxy contained stars of unprecedented energy and temperature, population 3 stars unlike any later observations revealed, or a colossally massive black hole at its center was ionizing everything around it with tremendous efficiency. In either case, the implication was clear. The universe became transparent far more rapidly than our models predicted. The process of reionization, which we believed occurred gradually over hundreds of millions of years, apparently proceeded in violent, chaotic bursts. Explosions of ionization spreading from centers of intense activity. A rough and turbulent transformation rather than a gentle evolutionary process. Our simulations had been wrong. Our understanding of how the early universe structured itself had been incomplete. These discoveries would have been sufficient to destabilize cosmology. But then the fundamental constant itself became unreliable. For years, the Hubble tension had been an irritant, a discrepancy that seemed to indicate either a measurement error or a minor gap in our models. When astronomers measured the universe's expansion rate using observations of the cosmic microwave background radiation, using information encoded in light from the earliest moments, they obtained a value: 67 kilometers per second per megaparsec. This measurement was extraordinarily precise. Yet when other astronomers measured the same expansion rate using direct observations of nearby galaxies and stars, they obtained a different value: 73 kilometers per second per megaparsec. The difference amounted to 9%. In ordinary science, 9% might be considered acceptable agreement. In precision cosmology, it is an astronomical gulf. Both measurements were extraordinarily accurate. The error margins were small. Too small to explain the discrepancy away. Somehow, the universe was expanding at different rates. The early universe according to one method. the modern universe according to another. This made no sense. The expansion rate should be predictable from any epoch. Webb was designed to resolve this question. With its unprecedented ability to measure distances with exactness, it could calibrate the cosmic distance ladder. It could verify which measurement was correct. Webb provided an answer, but not the hoped-for one. The telescope confirmed that the local measurements were accurate. The nearby universe expands at approximately 73 kilometers per second per megaparsec. Hubble was right. There was no error. The tension was not a measurement artifact. The tension was real, physical, fundamental. It represented a genuine discrepancy between the early universe and the modern universe. Something had changed. Something significant enough to alter the expansion rate itself. Something that contemporary cosmology had completely failed to account for. The implications reverberated through the field. If the fundamental behavior of the universe differs between epochs, then something profound occurs between the early universe and the modern one. Some physics, some event, some component of reality that standard models do not address. The foundations had shifted, the ground beneath cosmological certainty had become unsteady. As if to emphasize the magnitude of the crisis, the oldest structures in the universe demanded attention. Not individual galaxies, not collections of stars. Galaxy clusters, the largest nodes in the cosmic web. These entities form through gravitational assembly of smaller structures over billions of years. Like streams merging to form rivers, like rivers converging to create deltas. Hierarchical construction from small to large. According to the Lambda-CDM model, such massive structures should emerge quite late in cosmic history. They should not populate the early universe. The universe simply had not existed long enough for gravity to assemble such gigantic structures. Yet in late 2024, researchers working with Webb data identified a protocluster, the precursor stage to a giant galaxy cluster. Its age was troubling. When the universe had existed for only 650 million years, this structure had already begun assembling. A massive concentration of dark matter, already capable of hosting tens of thousands of galaxies, already containing dozens of newly formed galaxies within itself. The gravitational potential of this structure, its mass, its influence, exceeded predictions for that epoch by many orders of magnitude, by thousands of times what the models allowed. This was no small discrepancy. This was a direct contradiction of the hierarchy principle itself. According to the standard model, structures form from small to large. Gravity pulls them together gradually. Small halos merge. Larger structures emerge. Time is required. Billions of years. This protocluster had apparently never received that memo. It was born gigantic. It assembled at velocities that gravitational physics did not permit. The most fundamental mechanism of cosmic structure formation had been violated. When astronomers reviewed their simulations, they searched for errors. They expected to find computational mistakes. Instead, the data from 13 billion light-years away was transmitting a message across cosmic distances. Forget the story you have written. The universe operated differently than you supposed, and then everything converged, universe-breaking galaxies, impossible chemical enrichment, monster black holes arriving far too early, violent reionization happening too rapidly, expansion rate tensions between epochs, structure formation occurring too efficiently. These were not isolated anomalies. They were not unrelated problems. They were chapters of a single narrative. A narrative that suggested something fundamentally different about cosmic origins. The early universe was mature, not metaphorically, literally, observably, measurably, not in the gradual way our models predicted, not following the patient construction process that made sense to our understanding. The early universe appeared to have been seeded with structure, prepared, advanced, as if reality had undergone a preparatory phase before the Big Bang, and remnants of that phase persisted into our own universe. This realization represented a paradigm shift comparable to historical moments when our understanding of reality fundamentally transformed. In 1925, Edwin Hubble revealed that the Andromeda Nebula was not a cloud within our galaxy, but an independent galaxy itself, millions of light-years distant. In that moment, the universe expanded. What we had believed to be cosmic became provincial. The cosmos became incomparably larger than our previous conception. Webb's discoveries carried similar significance. The story of cosmic origins might have been not merely incomplete, but fundamentally wrong. The narrative might have extended further back. The universe might have been richer, more complex, more dynamic in its infancy than we imagined. These anomalies might not be failures of observation or glitches in measurement. They might be signatures of a more ancient cosmos, fingerprints of something that existed before our beginning. The implications crystallize when we consider what early universe maturity actually means. An early universe containing massive black holes cannot have been assembled only through the gradual accumulation processes we observe in the local cosmos. A universe containing abundant heavy elements must have undergone many stellar generations. A universe with fully formed galaxies of unusual size and complexity must have developed through extended processes of gravitational assembly and chemical enrichment, yet all this appears to have occurred before the standard timeline allowed. It appears to have occurred not through natural processes operating from initial simplicity, but through inheritance of conditions. Structures appear preformed. Chemistry appears pre-enriched. Gravitational potential appears prearranged. The early universe appears to have been arranged in some sense for complexity, as if history preceded our Big Bang, as if the universe did not truly begin from scratch but began with memory of something older. This is where Roger Penrose's controversial theory acquired new relevance. Consider what Penrose proposed. Each eon inherits structure from the previous one. The cycle is continuous. Information persists. Physical structures carry forward. The universe resets but remembers. And consider what Webb revealed. An early universe, impossibly mature, impossibly advanced, impossibly prepared. Could these observations represent not anomalies but inheritances? Could the early structures Webb detected be not products of our universe's own processes, but ghosts from the previous eon? Could the chemical enrichment, the black holes, the galaxies themselves be echoes of a cosmos that existed before our Big Bang? If so, then Hawking points, those predicted signatures of evaporating black holes from prior universes would not be random occurrences in the cosmic background radiation. They would have specific spatial correlations. They would cluster around the locations of early structures. They would reveal a pattern, a blueprint, a cosmic memory. Penrose and his colleagues announced they were re-examining the cosmic microwave background data in light of Webb's discoveries. This time they were not simply searching for temperature variations. They were looking for specific correlations, patterns that matched the locations and properties of the impossibly early galaxies and black holes Webb had found. The analysis continues. The results remain incomplete. But if correlations emerge, if patterns align, if the ancient light carries signatures of prior universes encoded in its temperature variations, then we will have discovered the greatest evidence for a fundamental truth. The universe as we know it is not the universe in itself. It is one breath in an infinite respiration, one cycle in an eternal return. What does it mean to live within such a cosmos? Consider the contrast between our individual existence and the existence of the universe itself. Each of us occupies perhaps 80 years, a fraction of an instant. An eon lasts 10 to the power of 100 years. A Google years, a number so vast our language fails. The ratio between these timescales is so extreme that mathematics becomes nearly useless for comparison. Where is our lifespan in relation to a Google year? We exist less than a single quantum of time in relation to an eon's duration, less than the smallest meaningful unit in cosmic accounting. Yet within our 80 years, we can contemplate the entire eon, we can write its equations, we can theorize about its beginning and end. Our minds, this 3-pound organ of biological neural networks, can encompass timescales a Google times our own duration. Our consciousness transcends time itself. This is the paradox of human existence. We are ephemeral, yet we are capable of understanding the eternal. Or consider the contrast between isolation and connection. The universe is profoundly, almost impossibly lonely. Galaxies separated by billions of light-years. Stars so distant they appear as pinpoints of light. The nearest star system, Alpha Centauri, requires 40,000 years to reach with our fastest spacecraft. The nearest large galaxy, Andromeda, lies 2.5 million light-years away. Beyond our reach. Beyond contact. Each galaxy, each star is like an island in an ocean of void. We are trapped on our world, confined by the speed of light, unable to traverse the distances that separate us from the cosmos around us. This is cosmic isolation, universal loneliness. And yet every atom within your body is connected to the furthest galaxies. The carbon in your molecules formed in stellar furnaces billions of years ago. The iron in your blood was created in the supernovae of ancient stars. The oxygen you breathe was forged in stellar cores. You are literally constructed from stardust. Not poetically, scientifically, factually. The atoms that constitute you traveled billions of years across the cosmos to assemble into your form. You are not separate from the universe. You are the universe examining itself. You are the cosmos-given consciousness. In the most profound sense, you are not alone. You were never alone. You are threaded through the entire cosmic tapestry. Consider further the contrast between helplessness and comprehension. We are physically vulnerable beyond description. A solar flare could collapse our civilization. A nearby supernova could sterilize our planet. A meteor impact could erase us. The forces of the cosmos operate according to their own laws with complete indifference to our existence. We cannot resist gravity. We cannot defy the expansion of space. We cannot escape the laws of thermodynamics. In a direct confrontation with the universe, we possess not even the power to resist meaningfully. We are dust before the wind, insignificant, powerless. Yet despite this physical helplessness, we possess intellectual power incomparable to anything else we know in the cosmos. We have deciphered the laws that govern black holes. We have mapped the geometry of space and time itself. We have traced the history of the universe backward to moments after its birth. We have written equations that describe the behavior of particles at scales smaller than atoms. We have created instruments that collect light that traveled for billions of years. We have transformed that light into images of the deepest cosmos. We have understood reality in ways that appear to exceed what any organism should be capable of comprehending. This is humanity's greatest victory, not dominion over nature, but comprehension of nature. Not power over the cosmos, but understanding of the cosmos. Consciousness is the mechanism through which the universe achieves self-awareness. In your quest for knowledge, you participate in the cosmos's ability to understand itself. There is another dimension to this crisis that deserves attention. The second law of thermodynamics. Entropy. Disorder. It is one of the most rigid laws of physics, supported by countless experimental observations. Order transforms into disorder. Buildings decay. Stars burn out. Coffee cools. The universe moves inevitably toward greater entropy, greater randomness, greater disorder. This is the direction of time itself. Entropy increases, always, without exception. Yet the Big Bang presents a profound puzzle. The universe began in a state of extraordinarily low entropy, a state of almost perfect order. The universe at its beginning was not just slightly ordered, it was exquisitely ordered. impossibly ordered. The probability of such an initial state arising randomly is absurdly small. Penrose calculated it precisely. The probability is smaller than 1 divided by 10 to the power of 10 to the power of 123. This is beyond astronomical. This is beyond any number that has conventional meaning. This is impossibility expressed mathematically. The standard model offers no explanation. It assumes a low entropy beginning. It does not explain why. Inflation theory describes the early universe's rapid expansion, but it assumes low initial entropy. It does not derive it. The problem remains unresolved within conventional cosmology, but Penrose's conformal cyclic cosmology provides a solution. During the transition between eons, the conformal transformation accomplishes something elegant. The gravitational entropy, the disorder of spacetime itself, measured through a quantity called the Weyl curvature, resets. The universe's geometric structure returns to an ordered state, not through some artificial imposition, not through adding assumptions. As a mathematical consequence of the conformal transformation itself, the geometry of the transition naturally produces low entropy in the next eon. It is not a special assumption. It is an inevitable result. This alone is remarkable. Of all the competing theories attempting to address cosmology's deepest mysteries, only conformal cyclic cosmology naturally explains the entropy of origins without requiring additional assumptions. The technical possibilities for explaining Webb's discoveries are multiple. Each has different implications. Direct collapse is one mechanism receiving serious consideration. In the conventional picture, a giant gas cloud fragments into thousands of pieces. These pieces form stars. The largest stars eventually explode, leaving behind black holes of modest mass. Over billions of years, these black holes grow by accreting surrounding material and merging with others. But under specific conditions, an alternative pathway becomes possible. The gas cloud collapses without fragmenting. Instead of breaking apart, it collapses as a single unified structure. This collapse proceeds directly to a black hole of tremendous initial mass, perhaps 100,000 solar masses, perhaps larger. Such a black hole would have a massive head start. Reaching 10 million solar masses becomes much more plausible if one begins with 100,000 instead of 100. What conditions enable such direct collapse? The gas must be nearly devoid of heavy elements. Heavy elements act as coolants. They promote fragmentation. Without them, the gas cloud remains hot. Heat resists fragmentation. It encourages collapse as a single unit. Additionally, intense radiation from neighboring sources is needed. This radiation breaks up hydrogen molecules. It prevents the gas from cooling too efficiently. Two mechanisms, both preventing fragmentation, both allowing direct collapse. This scenario is attractive because it requires no new physics beyond what we already know. It only requires unusual initial conditions, conditions that may have been common in the early universe but are rare today. An even more speculative possibility: primordial black holes. These hypothetical objects would not form from stellar death. They would have been born in the first second after the Big Bang, from quantum fluctuations in the density of the early universe, from density variations in space itself. Imagine the newborn universe as turbulent water. Bubbles form and collapse everywhere. Most vanish. But if a density fluctuation is sufficiently large and concentrated, it collapses into a black hole. Not from a dying star, from the grain of reality itself. Such objects could have a wide range of masses, from asteroidal to stellar to supermassive, and critically, they would not require stellar processes to exist. They would be born with the universe. They would have billions of years to grow by accreting surrounding material. They could be the ancestors of the 10 million solar mass monsters Webb has observed. We possess no direct evidence for primordial black holes yet, but the laws of physics permit them. The early universe, as revealed by Webb, appears to have been bumpy. filled with density fluctuations. If inflation theory produces a perfectly smooth universe, yet Webb shows evidence of structure and non-uniformity, perhaps primordial black holes are part of the answer. Perhaps they constitute a portion of dark matter itself. Perhaps a single population of exotic objects can solve multiple cosmological puzzles simultaneously. Early dark energy is another framework gaining attention. The cosmological constant, that value Einstein reluctantly added to his equations, is typically treated as truly constant. But what if dark energy, the force driving cosmic acceleration, was not constant throughout history? What if in the first moments after the Big Bang, dark energy had a different value, a higher value? Such early dark energy would have accelerated cosmic expansion intensely. Then it might have decayed, reduced to the lower value we observe today. This could alter the transitions between different cosmic eras. It could affect structure formation. It could potentially explain the Hubble tension. But such scenarios require new physics, new particles, new fields, new forces beyond the standard model of particle physics. They move us into speculative territory. These mechanisms, direct collapse, primordial black holes, early dark energy, are not mutually exclusive. Perhaps multiple processes operated simultaneously. Perhaps the early universe was populated by primordial black hole seeds that then grew through accretion and direct collapse processes. Perhaps dark energy played a role in determining the conditions under which these processes operated. All these mechanisms point toward the same conclusion. The early universe operated according to different rules than those we observe today. Or the early universe inherited conditions that produced different outcomes. Or something about the universe's origin differs fundamentally from what standard models propose. Consider the implications if Penrose's theory proves correct. If cyclic cosmology is true, then time does not have a beginning. The concept of creation becomes meaningless. There is no moment when non-existence transitions to existence. There are only eons, cycles following cycles, eternally. For physics, this would represent a fundamental reconceptualization. Every mystery about initial conditions, why the universe began with low entropy, why it appears fine-tuned for complexity, why fundamental constants possess their particular values, would gain potential solutions. Each eon inherits from the previous one. Structures form from the legacy of the past. Initial conditions are not arbitrary. They arise from the previous cycle's ending. For philosophy, the implications are even more profound. The universe would become eternal. Existence would not be contingent on a moment of creation. Being would be fundamental. The cosmos would be self-explaining. No external cause would be required. No divine origin would be necessary. Reality would simply be, eternally cycling, forever renewing itself. For theology and spirituality, the implications are more complex. If the universe is eternal and self-sustaining, then the role of creator becomes reconceptualized. Some traditions have always conceived of divinity as existing beyond time, outside the temporal flow. An eternal universe might fit more comfortably within such frameworks. These are not merely academic questions. They touch the deepest questions of existence. Why is there anything rather than nothing? Why does the universe possess the properties it does? Why do we exist? What unites all these alternative theories? Conformal cyclic cosmology, ekpyrotic models involving colliding branes in higher dimensional spaces, loop quantum gravity with its quantum bounces and discrete spacetime is remarkable. Despite beginning from entirely different mathematical starting points, despite employing completely different frameworks, they arrive at similar conclusions. The Big Bang was not an absolute beginning. It was a transition. Time extends beyond it. The universe has history deeper than we previously conceived. But all face common challenges. All must grapple with the second law of thermodynamics. All must explain how information transfers between cycles. All must account for why observable reality appears to proceed from an extremely low entropy state Standard cosmology has never adequately addressed this problem. These alternative theories at least attempt solutions. Now we must confront the personal implications. You exist in a universe far stranger and more mysterious than previous generations understood. The foundations of cosmological knowledge have shifted. Models that seemed secure, that explained observations, that answered fundamental questions, these models are failing. The telescope that was built to confirm our theories instead reveals how incomplete they are. This might generate despair. It might seem that all our understanding is illusory. Every answer is provisional. Every explanation is contingent. How can we trust anything if the universe refuses to conform to our theories? But this perspective misses something crucial. This is how science progresses. This is how we approach truth. Not through claiming certainty, but through recognizing uncertainty. Not through defending outdated theories, but through questioning them. Not through resting in answers, but through asking better questions. The universe does not owe us simple explanations. It does not conform to our desires for neat, comfortable understanding. It reveals itself gradually, reluctantly, often in ways that challenge and disturb us. This is not a weakness of science. It is the strength of science. Science is the organized pursuit of knowledge through systematic questioning. Science advances not when we know more, but when we recognize how much more we don't know. You live in the era when this recognition is happening. You are witnessing the moment when paradigms shift, when knowledge transforms, when the universe reveals itself as more complex, more strange, more beautiful than we previously imagined. Consider what this means for your own sense of understanding. Your education taught you certain foundations. You learned the story of cosmic origins, the establishment of physical laws, the history of structure formation. That story seemed settled, confirmed by observations, supported by mathematics. It provided a framework for comprehending your place in the cosmos. Now that framework trembles. The observations that seem to confirm it instead contradict it. New phenomena appear that the framework cannot accommodate. The telescope designed to resolve remaining questions instead multiplies the mysteries. This is disturbing. It challenges the security we seek from knowledge. It demonstrates the provisional nature of all human understanding. But it also reveals something profound. It shows that the pursuit of truth is not the accumulation of permanent facts. It is an ongoing dialogue with reality. Reality constantly reveals new facets. Reality refuses the neat categories we impose upon it. Reality is stranger, richer, more elaborate than any theory we construct. To accept this is to mature intellectually, not to despair at uncertainty, but to embrace it as the frontier of genuine knowledge. Not to defend outdated frameworks, but to question them even when they seem successful. Not to rest in answers, but to find meaning in the questions themselves. The observations continue. Webb remains in orbit, collecting photons that have traveled billions of years across expanding space. Each photon carries information. Each light source reveals structure and process. Each discovery poses new questions. What will the next anomalies be? What structures will we find in deeper space, in more ancient times? What patterns will emerge as we map the universe's childhood in ever greater detail? And as these discoveries accumulate, as the data mounts, as the picture becomes clearer, what will we learn about our own place in this cosmos? What truths about human existence will be revealed? One certainty exists. Whatever we discover, it will be stranger than we expect. It will challenge us. It will demand new frameworks. It will force us to expand our understanding of what is possible. This is the gift of instruments like Webb. Not certainty, but expanded possibility. Not final answers, but deeper questions. Not comfort, but encounter with the profound mystery of existence. A universe that cycles through countless eons. A cosmos that may carry memory from one cycle to the next. A reality that may have no beginning and no end. Physical structures that should be impossible, appearing exactly where theory says they cannot exist. laws that seem to change, constants that vary, a cosmos that refuses the neat explanations we construct for it. This is the universe Webb reveals. This is the universe in which we find ourselves. And perhaps this is the point we must ultimately confront, not as observers of the cosmos, but as participants in it. Your atoms are part of this story. Your consciousness is part of this unfolding. Your questions, your wonderings, your attempts to understand, these are the universe's own process of self-comprehension. You are not separate from the cosmos. You are not observers standing outside looking in. You are embedded within it. You are made of it. You are the cosmos made conscious. In that recognition lies the deepest significance of Webb's discoveries. Not in the individual galaxies or black holes or chemical abundances, but in what they reveal about our fundamental nature. We are not external to the universe, we are aspects of it. The universe achieves understanding through us. This is not metaphor, this is physics. Consciousness emerges from physical processes. These processes are part of the cosmos. The cosmos uses those processes to know itself. And so, when you look at the images from Webb, when you read about the impossibly early galaxies, when you contemplate the implications of cyclic universes and previous eons, you are not merely learning about something external. You are learning about yourself, about what you are made of, about where you come from, about your connection to everything that exists. This is the true crisis and transformation that Webb has catalyzed. Not merely a revision of cosmological models, not merely an overturning of theoretical expectations, but a fundamental shift in how we understand our own place within the cosmos. We are the universe thinking about itself. We are the cosmos become conscious. And what lies at the end of this awareness? What truth awaits when we finally understand ourselves fully? Perhaps the greatest discovery ahead is not about distant galaxies or black holes or the structure of spacetime. Perhaps it is about ourselves, about what we are capable of understanding, about what we are capable of becoming. The universe is asking these questions through you. It is asking them through every person who has ever looked up at the night sky and wondered. Every person who has pursued understanding despite the vastness of what remains unknown. Every person who has dared to question established frameworks and imagine alternatives. In asking these questions, we do not merely engage in abstract intellectual exercise. We participate in the universe's own process of self-discovery. We become instruments through which reality knows itself more completely. We become part of the mechanism by which the cosmos achieves expanded consciousness. The cosmos was supposed to be solved. We spent decades designing, building, and calibrating the ultimate looking glass, launching it into the deep freeze of space with a singular mission: to confirm the grand blueprint we had spent a century drawing. The standard model of cosmology was our intellectual crown jewel, a beautifully orchestrated timeline that neatly filed away the birth of space, the ignition of the first stars, and the slow, majestic assembly of galaxies over 13.8 billion years. It was a perfect story. But when the James Webb Space Telescope opened its gilded eye, it didn't deliver confirmation. It delivered a crisis. The data streaming back across the infrared spectrum didn't just nudge the boundaries of modern physics, it shattered them. Everywhere Webb pointed, it found a mature, highly developed, and chemically ancient universe existing at a time when the cosmos should have been nothing more than a dark, chaotic nursery. The math that had held our reality together for generations suddenly went bankrupt. Galaxies that should have been tiny, disorganized clumps of gas were appearing as fully formed giants, 10 to 100 times more massive than the timeline allowed. Cosmic monsters, black holes weighing tens of millions of suns, were sitting comfortably in the dawn of time, defying the physical speed limits of how matter can accumulate. Elements like carbon and oxygen, which require generations of stellar life and death to forge, were already polluting the earliest stellar systems. It was an impossible reality and cosmic insult to our models of stellar evolution. But the most unsettling realization, rippling through the scientific community, is that these staggering anomalies might not be a collection of random errors. Instead, they form a perfect mathematical bridge to a radical, mind-bending theory championed by one of the greatest mathematical physicists of our time, Sir Roger Penrose. To understand why modern astronomy is facing an existential meltdown, you have to understand the story we told ourselves for decades. The orthodoxy stated that everything, time, space, matter, and energy, burst into existence from an infinitely hot, infinitely dense singularity 13.8 billion years ago. We called it the Big Bang, though the name is notoriously misleading. It wasn't an explosion expanding outward into a pre-existing empty room. There was no room. Space itself was the thing expanding. This narrative wasn't just a wild guess. It was supported by the cosmic microwave background radiation, the ancient, faded thermal echo of the birth of the universe. For years, this faint glow, uniform in every direction, served as the ultimate proof of our cosmological timeline. But as our measurements grew more precise, tiny hairline fractures began to spiderweb across this pristine model. These weren't dramatic, explosive failures of logic, but subtle discrepancies that suggested something foundational was missing from our equations. And it is precisely within these subtle cracks that Roger Penrose found the doorway to a completely different reality. Penrose is not a fringe theorist. He is the architect of our modern understanding of spacetime, earning the 2020 Nobel Prize for proving that black holes are an inevitable, mathematical certainty of Einstein's general relativity. He showed that under normal astrophysical conditions, space and time must inevitably break down into a singularity. But after a lifetime of studying these breaking points, Penrose looked at the ultimate singularity, the Big Bang, and proposed an idea that shocked the physics world: Conformal cyclic cosmology, or CCC. Penrose argued that the universe has no true beginning and no ultimate end. Instead, it moves through an infinite succession of cosmic cycles called eons. Each eon kicks off with a hot, dense, Big Bang-like state, expands and cools over trillions of years, and eventually dissolves into an absolute vacuum populated only by massless particles. In this ultimate state of cosmic decay, something extraordinary happens. When the universe contains nothing but massless photons, the concepts of distance and time completely evaporate. A photon experiences no time. For light, the moment of emission and the moment of absorption are identical, whether they are separated by an inch or a billion light-years. Without mass, there are no clocks and no rulers. And in the elegant language of conformal geometry, a universe with no scale changes everything. When you strip away scale, an infinitely expanded, cold, empty cosmos becomes mathematically identical to an unimaginably compressed, hot, dense new beginning. The death of the old universe smoothly, seamlessly maps onto the Big Bang of the next, without any breakdown of physical laws. This wasn't just a beautiful mathematical trick. Penrose claimed it left physical scars. He argued that the violent events of a previous universe would leave ghosts in our own, specifically in the cosmic microwave background. When supermassive black holes from the prior eons slowly evaporated over a googol years via Hawking radiation, their final, cataclysmic releases of energy would be carried through the conformal transition. In our universe, this energy would manifest as distinct concentric rings of temperature variation, cosmic echoes Penrose dubbed Hawking points. When he published this claim in 2010, the mainstream scientific community pushed back hard, writing off the patterns as statistical noise, or the result of looking so hard for a pattern that you inevitably find one in random data. The debate stalled, trapped in a mathematical stalemate. Mainstream cosmology largely ignored the cyclical model, confident that their standard timeline would be vindicated once we could see clearly into the deepest past. Then came December 2021. The deployment of the James Webb Space Telescope was meant to settle the scores. Equipped with an enormous, gold-coated primary mirror capable of piercing the cosmic dust and capturing highly redshifted infrared light, Webb could see structures that existed when the universe was just a few 100 million years old, a realm where its predecessor, Hubble, was completely blind. But instead of revealing a smooth, gradual construction process where dark matter slowly gathered pristine hydrogen gas to ignite the very first primitive stars, Webb revealed a cosmos that was already running a marathon. In early 2023, astronomers boggled at data revealing universe-breaking galaxies. These stellar systems, existing less than 500 million years after the starting gun of creation, were as massive and structurally mature as mature galaxies today. The standard framework of cosmology provided no mechanism to drag that much matter together so quickly. The chemical timeline collapsed next when Webb analyzed the light from Maisie's galaxy, dating back to just 390 million years after the Big Bang. The spectrographs detected an unmistakable chemical signature: oxygen. This was a logical catastrophe. Heavy elements like oxygen do not get made in a Big Bang. They must be cooked in the nuclear bellies of massive stars, blasted out into space via supernovae, cooled, recondensed into a second generation of stars, and processed all over again. Our best models insisted this chemical enrichment takes at least 500 million to 1 billion years to achieve. Yet here it was, vibrant and abundant, sitting in a universe that was barely a fraction of that age. The cosmos was acting chemically old while chronologically an infant. The anomalies only deepened with the discovery of the little red dots, mysterious, highly compact objects saturating the early universe. Analysis revealed they weren't typical galaxies at all, but supermassive black holes boasting masses of 10 million suns, actively gorging on surrounding matter. According to the Eddington limit, which dictates how fast a black hole can feed before its own radiation pressure chokes off its food supply, growing a seed black hole to this scale should take billions of years. Webb's discovery forced physicists to consider radical alternatives. Did these monsters skip the star phase entirely through a process called direct collapse, where a colossal gas cloud falls inward all at once to birth a massive black hole seed? Or were they primordial black holes, formed not from stars but from violent density fluctuations in the literal first seconds of the universe's existence? Every layer of the early cosmic structure seemed to defy the rules. Consider JWST 14-0, a galaxy observed deep within the era of reionization, a time when the universe was supposed to be choked by an impenetrable fog of neutral hydrogen gas that absorbed ultraviolet light. Yet, Webb detected brilliant Lyman alpha emissions from this ancient system, meaning the galaxy had somehow punched a transparent bubble over 600,000 light-years wide through the cosmic mist. The sheer energy required to clear such an enormous space at that time implied stellar activity or black hole radiation vastly more potent than anything mainstream simulations had ever accounted for. And then, the hairline cracks in our cosmic expansion models widened into a chasm. The Hubble Tension, the frustrating 9% discrepancy between how fast the early universe says we should be expanding versus how fast the local universe actually is expanding, was supposed to be a calibration error. Mainstream cosmologists wagered that our measurements of local Cepheid variable stars were flawed. Webb was tasked with auditing the data. Its ultra-sharp infrared vision confirmed a local expansion rate of 73 kilometers per second per megaparsec with absolute certainty, while the early universe data held firm at 67. The tension wasn't a mistake. It was a profound, undeniable reality. The early universe and the late universe are operating under different rules, signaling a fundamental gap in our understanding of cosmic evolution. The ultimate defiance came from the largest scales of reality. According to hierarchical structure formation, gravity works from the bottom up. Small halos merge into galaxies, which slowly drift together to form clusters over billions of years. But Webb spotted a massive protocluster, the sprawling gravitational foundation of a future cosmic metropolis, existing just 650 million years after the Big Bang. This colossal web of dozens of galaxies assembling around a massive dark matter core should not have been there. It was like finding a fully realized skyscraper built before the foundation of the surrounding city had even been cleared. When you piece these cosmic puzzles together, the mature galaxies, the chemically enriched gas, the impossible black holes, the shifting expansion rates, and the premature galaxy clusters, the architecture of standard cosmology begins to bend under the weight of its own contradictions. The universe Webb is showing us is faster, wilder, and radically more mature than our linear timelines ever permitted. We are left standing at a profound crossroads in scientific history. We can continue to patch a straining model with increasingly complex, ad hoc assumptions, or we can entertain the staggering alternative whispered by the mathematics of Sir Roger Penrose, that the reason the early universe looks so mature, so filled with ancient elements and monster black holes, is because it isn't a beginning at all. It is a continuation. The cosmic dawn we are peering into may simply be the twilight of a reality that came before, preserved across the threshold of an eternal cycle. To peer into this alternative cosmic framework is to completely re-engineer our understanding of how structure, matter, and information are preserved across what we once considered an absolute barrier. If the standard model is a single, linear tape that began at a definitive 0 point, Penrose's conformal cyclic cosmology forces us to view our universe as a single frame in an infinite cinematic reel. The profound anomalies delivered by the James Webb Space Telescope are no longer isolated paradoxes or inconvenient data points to be brushed aside with ad hoc adjustments to dark matter behavior. Instead, they transform into the natural, predictable consequences of a cosmos that possesses a deep, structural memory of its past life. The fundamental breakdown of the standard timeline always returns to the problem of time itself. When Webb identifies an ultra-massive black hole or a highly enriched galaxy at a redshift that places it a mere 300 million years after the Big Bang, our immediate reaction is to try and accelerate our modern physical mechanisms. We attempt to force gas clouds to collapse faster, we push the limits of how rapidly stars can burn through their fuel, and we invent highly speculative pathways, like hypercritical accretion, to justify how a seed black hole can bypass its own radiative speed limits. But what if the flaw is not in the speed of the mechanisms but in our assumption of the starting line? If the Big Bang was not the absolute generation of everything from nothing, but a conformal transition from an endlessly expanded previous eon, the cosmic landscape changes entirely. To see how this works mathematically, one must look at the behavior of spacetime at the extreme boundaries of an eon. In the deep, far future of a dying universe, trillions of years from now, all conventional matter will have dissolved. Stars will have long since ceased their fusion, cold iron remnants will have decayed, and even the most massive black holes will have completely vanished into an ocean of Hawking radiation. What remains is a cosmos populated entirely by massless entities, photons and perhaps gravitons. For a universe containing exclusively massless particles, the metric of spacetime loses its physical grip. Because mass is the anchor that allows us to define scale, a universe without mass is a universe without an intrinsic sense of size. A single millimeter and a billion light-years become physically indistinguishable, because there are no longer any atomic structures, no rulers, and no clocks to define the difference. This scale invariance allows for a conformal mathematical transformation. Through this geometric smoothing, the infinite, cold, empty future of that dying eon can be mathematically squeezed and matched perfectly onto the hot, dense, infinitely compressed beginning of a subsequent eon. The boundary between the two is not a chaotic singularity where the laws of physics explode into infinity and cease to make sense. Instead, it is a smooth, continuous surface, a three-dimensional space-like hypersurface that acts as a bridge. The equations of general relativity do not crash. they pass through this boundary seamlessly. The immediate implication of this transition is that information, energy, and structural imprints can survive the journey. While the extreme heat and density of the new eon's dawn would wipe away the vast majority of local configurations, melting macroscopic structures back into a primal plasma, it cannot completely erase the largest-scale gravitational and energetic disruptions of the previous era. The most dramatic of these disruptions are born from the deaths of the previous universe's most terrifying residents, supermassive black holes. When a supermassive black hole sits in the cold vacuum of an expanding universe, it slowly, agonizingly bleeds mass into the surroundings via quantum fluctuations at its event horizon. This Hawking radiation is incredibly faint, but over a span of time that dwarfs our current cosmic age by scores of orders of magnitude, the black hole eventually pops out of existence in a final, concentrated burst of pure energy. In the Standard Model, this radiation simply dissipates into an infinite dead void, achieving nothing. But in a cyclical model, that massive deposit of energy, concentrated at a specific point in the dying cosmos, is carried across the conformal boundary. Because the infinite future is mapped onto the new beginning, these specific points of cataclysmic evaporation project directly into the initial plasma of our Big Bang. Penrose terms these cosmic scars Hawking points. As the new universe undergoes its initial phase of expansion and cooling, the intense concentrations of energy originating from these Hawking points would create localized, expanding spheres of thermal and gravitational disruption in the early plasma. When the universe finally cools enough to become transparent, roughly 380,000 years after the transition, the photons escaping from these disrupted regions would bear a permanent mark. To our instruments, these would appear as highly specific, concentric rings of temperature fluctuation imprinted upon the cosmic microwave background. For over a decade, the search for these rings was treated as a fringe mathematical exercise. The datasets provided by satellites like WMAP and Planck were scrutinized, but mainstream cosmologists argued that any patterns found were merely statistical artifacts, the cosmological equivalent of seeing faces in the clouds. Because our Standard Model insisted that the cosmic microwave background must be perfectly random, born from quantum fluctuations during a brief epoch of cosmic inflation, any non-random concentric structures were dismissed as bad data or flawed analysis. But Webb's discoveries have destabilized this dismissive complacency. By revealing a universe that is systematically too mature across multiple independent lines of observation, the telescope has forced a re-examination of theories that allow for pre-existing structure. If Webb shows us that the early universe didn't start as a perfectly smooth, featureless canvas, then the search for structured anomalies in the cosmic microwave background gains an entirely new level of urgency. The concentric rings calculated by Penrose and his collaborators cease to be mathematical curiosities. They become the prime candidates for explaining the uneven, highly accelerated starting conditions of our cosmos. Consider the problem of the universe breaking galaxies through this lens. In the standard cosmological framework, the distribution of matter in the infant universe is incredibly uniform. For galaxies to form, gravity must painstakingly pull together microscopic variations in density over hundreds of millions of years. This bottom-up construction is a slow, methodical process. But if the conformal boundary carries over large-scale gravitational waves and density perturbations from the supermassive structures of a prior aeon, the new universe does not start from a blank slate. It starts with a massive, pre-installed blueprint of gravitational sinks. These pre-existing fluctuations would act as hyperpotent cosmic seeds. Rather than waiting for dark matter to slowly pool together under its own weak gravitational attraction, gas in the early universe would be violently and efficiently channeled into massive, predetermined gravitational wells left behind by the previous eon. This would fundamentally bypass the traditional timeline for galaxy assembly. It explains why Webb can look at an epoch when the universe was only a few 100 million years old and find galaxies that possess the mass, structural definition, and starlight output of systems that should have taken billions of years to mature. They didn't grow quickly within our timeline. They were jump-started by the structural inheritance of a past universe. This structural inheritance also provides a radical, yet elegant solution to the mystery of the early supermassive black holes. The presence of black holes weighing millions or even tens of millions of solar masses within the first several 100 million years of time is perhaps the most glaring contradiction Webb has uncovered. Under the Standard Model, a black hole must begin its life as a stellar remnant, a seed of perhaps a few dozen to 100 solar masses created when a massive star collapses. To reach the scales Webb is observing, these seeds would have to swallow surrounding gas at a rate that completely violates the laws of radiation pressure, or they would have to merge with thousands of other black holes in an impossibly short window of time. The alternative theories currently being debated by mainstream physicists, such as the direct collapse of pristine gas clouds or the creation of primordial black holes during an inflationary phase, are desperate attempts to solve the time problem within a strictly linear universe. Direct collapse requires incredibly specific, pristine conditions where gas is kept hot by external radiation so it can bypass star formation and fall directly into a monster seed. Primordial black holes require quantum fluctuations during inflation to be tuned to an absurdly precise degree to trigger immediate gravitational collapse in the first fractions of a second. But in conformal cyclic cosmology, the presence of early, massive black holes is an intrinsic feature of the model. While the conformal transition strips away mass and scale from the contents of the universe, the gravitational information, the extreme distortions of spacetime geometry caused by the previous aeon supermassive black holes is not entirely lost. The intense localized concentrations of energy transferred through the Hawking points would create ideal conditions for the immediate, instantaneous formation of massive black hole seeds at the very dawn of the new eon. These wouldn't be stellar remnants trying to grow against the clock. They would be primordial giants, born directly from the concentrated energetic debris of the previous universe's final days. They would possess a massive head start, allowing them to sit comfortably at the centers of the earliest galaxies, actively feeding on the abundant gas of the young cosmos, and presenting themselves to Webb's infrared mirrors as the enigmatic little red dots. This brings us to the shocking collapse of the chemical timeline. The detection of heavy elements like carbon, nitrogen, and especially oxygen in galaxies like Maisie's galaxy or Jade's GSZ 14-0 has sent shockwaves through the cosmochemistry community. The absolute rule of stellar nucleosynthesis is that the Big Bang only produces the lightest elements, hydrogen, helium, and a trace amount of lithium. Every single heavier atom on the periodic table must be forged inside the hearts of stars. For a galaxy to exhibit high levels of oxygen enrichment, it must have already hosted generations of massive stars that lived, exhausted their fuel, exploded as supernovae, and seeded the surrounding interstellar medium with their processed interior matter. When Webb detects abundant oxygen in a galaxy viewed at a time when the universe was less than 400 million years old, the traditional math simply breaks. Even if the very first generation of stars, the hypothetical hypermassive population 3 stars, formed immediately and died rapidly, they would not have had enough time to cycle their matter through the interstellar medium, enough times to produce the chemical maturity Webb is recording. The early universe looks chemically old because, according to our linear models, it should require far more time to accumulate those elements. However, if we entertain a cyclical framework, the mystery of this premature chemical maturity takes on a completely different dimension. While the physical atoms of the previous universe would be broken down into their fundamental massless constituents during the ultimate expansion and subsequent conformal compression, the energy densities and structural fluctuations carried across the boundary would dictate how the primal matter of the new universe behaves. If the starting plasma is highly structured, uneven, and subjected to localized pockets of extreme energy from the previous eon's remnants, the rate of initial star formation and subsequent nuclear processing would be radically accelerated. The universe would not undergo a slow, gentle transition from simple hydrogen gas to complex chemistry. Instead, the intense, highly compressed energetic conditions inherited from the past would trigger a violent, hyper-efficient burst of stellar life and death. The cosmos would appear chemically mature almost instantly because its very foundation was laid by an energetic framework that had already spent an eternity evolving. This interconnectedness of anomalies extends directly to the largest structures in the cosmos, the galaxy clusters. The discovery of a fully developing protocluster at a redshift corresponding to 650 million years after the Big Bang is a direct challenge to the bottom-up paradigm of structure formation. In a standard universe, you cannot build a city before you build the houses. You cannot have dozens of galaxies gravitationally bound and interacting within a massive dark matter halo at that early epoch, because the universe simply hasn't existed long enough for gravity to propagate across those immense distances and pull those structures together. It is a mathematical impossibility within the constraints of the standard Lambda-CDM model. Yet, if the distribution of matter is being guided by a pre-existing cosmic web inherited from the conformal mapping of a prior eon, this top-down anomaly becomes perfectly logical. The grand nodes of the previous universe's structure, the places where matter and supermassive black holes clustered over trillions of years, leave an indelible gravitational imprint on the conformal boundary. When the new eon begins, matter does not accumulate randomly. It falls directly into these pre-existing grand-scale structural troughs. Skyscraper-scale structures form concurrently with, or even prior to, the individual stellar systems within them. The protocluster Webb observed is not an impossible anomaly that defied hierarchical growth. It is the visible manifestation of a cosmic framework that is operating on a scale of time that spans far beyond 13.8 billion years. And it is here that we find the true significance of the Hubble tension, the persistent 9% discrepancy in the expansion rate of the universe that Webb has definitively confirmed to be real. For years, cosmologists treated this tension as a nagging detail, a minor disagreement between two measurement techniques that would eventually be resolved by better calibration. But Webb's ultra-precise verification of the local expansion rate has turned this minor disagreement into a full-blown structural crisis. The fact that the early universe, as measured through the cosmic microwave background, insists on an expansion rate of 67 kilometers per second per megaparsec, while the local universe stubbornly expands at 73, means our fundamental equations are missing a core component. This discrepancy is a smoking gun for new physics. It tells us that the relationship between the early universe and the late universe is not a simple, unbroken linear progression governed by a constant amount of dark energy and dark matter. Something is changing, shifting, or injecting energy into the system over cosmic time. In a standard, closed-loop linear model, this requires the invention of exotic, hypothetical entities like early dark energy or decaying dark matter, components that exist solely to fix the math without any independent physical justification. But in conformal cyclic cosmology, the changing dynamics of space and time are built into the very geometry of the system. The universe is constantly transitioning between states where mass dictates the scale of reality and states where masslessness erases it. The expansion of our current universe is not just an isolated event driven by an arbitrary cosmological constant. It is a phase within a larger geometric cycle. The tension between the early and late universe measurements could easily be the result of our equations trying to force a purely linear framework onto a spacetime geometry that is subtly curving and preparing for its ultimate, long-term conformal transition. The discrepancy isn't an error in our instruments. It is the friction created by forcing a cyclical reality into a linear box. The James Webb Space Telescope was built to answer our oldest questions. But its true triumph is that it has forced us to ask entirely new ones. It has taken the pristine, comfortable orthodoxy of modern cosmology and exposed its limitations. Everywhere it looks, it reveals a cosmos that refuses to behave like a newborn infant. It shows us an early universe that is heavy with mature galaxies, polluted with complex chemical elements, dominated by ancient supermassive black holes, and structured on scales that defy our timelines. We can no longer pretend that a few minor adjustments to our existing models will make these anomalies go away. The hairline cracks have shattered the glass. We are standing at a precipice where our understanding of time, space, and the very origin of reality must expand. Whether Penrose conformal cyclic cosmology is the final, definitive answer remains a subject of intense mathematical and observational debate. But what Webb has proven beyond a shadow of a doubt is that the standard story is no longer enough. The Big Bang was not the definitive absolute beginning of our reality. It was merely a horizon, a grand, fiery curtain rising on an act that is part of a much older, much grander, and completely endless cosmic play. To fully appreciate the scale of this cosmological crisis, we must look at how the James Webb Space Telescope's discoveries have fundamentally reignited the fiercest debate in modern physics, the battle between the inflationary paradigm and, quote, cyclical eternity. For the last 40 years, the standard narrative was kept alive by a theoretical mechanism known as cosmic inflation. This theory suggested that a fraction of a second after the Big Bang, the universe underwent an exponential burst of expansion, stretching space by a factor of 10 to the power of 26 in a blink of an eye. Inflation was the ultimate cleanup tool for cosmology. It explained why the universe looks so flat, why the temperature of the cosmic microwave background is so uniform, and why we don't see exotic defects like magnetic monopoles. But inflation also demanded a clean slate. It insisted that any structural memory of whatever existed before the Big Bang, if anything existed at all, was violently ripped apart, diluted, and smoothed out into absolute nothingness. The only structures allowed to exist after inflation were random, microscopic quantum fluctuations that were stretched to astronomical scales, eventually acting as the seeds for galaxies. For decades, this was the undisputed gospel. If you questioned inflation, you were questioning the very foundation of modern astrophysics. Yet, the mature universe Webb is presenting to us acts as a direct, physical counter-argument to this forced amnesia. When Webb reveals galaxy clusters already assembling at a redshift where inflation dictates there should only be diffuse gas, it implies that the primordial seeds were not perfectly random, microscopic fluctuations. Instead, the seeds of these cosmic structures appear to have been massive, structured, and highly concentrated from the literal beginning of our timeline. This is where the inflationary paradigm begins to buckle, and where Penrose's conformal cyclic cosmology provides a seamless alternative. In a cyclical universe, you do not need an ad hoc inflationary event to explain why the universe is flat or uniform. The uniformity and flatness are inherited from the infinite expansion of the prior eon. By the time a universe reaches the end of its life cycle, trillions of years from now, it has expanded so thoroughly that its geometry is completely flat, and its contents are perfectly distributed. When the conformal transformation takes place, mapping this infinite, smooth future onto a new, hot Big Bang, that flatness and uniformity are naturally preserved. Crucially, however, the conformal transition does not erase the massive gravitational signatures left behind by the previous universe's supermassive black holes. It acts as a filter, clearing away the microscopic clutter of the old universe while allowing the grandest, most energetic gravitational blueprints to pass through intact. This concept of structural preservation across an entire cycle of reality completely redefines the nature of dark matter and dark energy, two of the most elusive placeholders in modern science. In the Standard Model, dark matter is treated as a hypothetical, undiscovered subatomic particle that provides the extra gravitational glue needed to hold galaxies together. Dark energy is treated as a mysterious fluid or a constant energy density inherent to space itself, driving the accelerated expansion of the cosmos. Together, they make up 95% of everything that exists, meaning that under the Standard Model, we are fundamentally ignorant about the nature of the vast majority of our universe. But what if these placeholders are actually the geometric ghosts of the previous aeon? In conformal cyclic cosmology, the equations that govern the transition from one eon to the next introduce subtle geometric terms that behave exactly like dark matter and dark energy. For instance, the gravitational waves generated by the collision of supermassive black holes in the prior universe would create permanent, oscillating ripples in the conformal boundary. When matter begins to form in the new eon, it would naturally pool within these invisible, pre-existing geometric ripples. To an astronomer using standard instruments, it would appear as though some invisible, non-interactive dark matter particle is pulling the gas together. In reality, the gas is simply responding to the deep, historical curves imprinted on spacetime by the titans of a forgotten universe. Similarly, dark energy ceases to be an unexplained, magical pressure pushing space apart from the inside. Instead, it becomes a structural characteristic of a cyclical spacetime metric. The accelerated expansion we observe today is the geometric momentum of our eon driving us toward our ultimate, mass-free future. It is the universe preparing itself for the next scale-invariant transition. The 9% discrepancy highlighted by the Hubble tension is the physical manifestation of this transition in action. When we measure the early universe via the cosmic microwave background, we are looking at a system that is still highly constrained by the lingering energetic densities of the conformal boundary, yielding a slower expansion rate of 67. But when we look at the local modern universe, we are seeing a system that has broken free from those early constraints and is rapidly accelerating toward its mass-free destiny at 73. The tension is not a crisis of measurement error. It is the fingerprint of cosmic evolution moving across an epic cyclical arc. To see this transformation in action, we can look at how Webb's data is forcing scientists to completely rewrite their simulations of the cosmic dawn. For years, supercomputer simulations of the early universe produced predictable results. A dark, quiet epoch where pristine clouds of hydrogen and helium slowly cooled over hundreds of millions of years. The first stars to ignite, known as population 3 stars, were thought to be solitary giants, hundreds of times more massive than our Sun, burning pure hydrogen and dying in spectacular supernovae within a few million years. These explosions were supposed to slowly pepper the pristine space with the very first hints of heavier elements, setting the stage for a tedious, multi-billion-year chemical evolution. But Webb has shattered this slow-motion fairy tale. By discovering highly enriched galaxies containing complex elements like oxygen and carbon at a mere 300 to 400 million years after the Big Bang, the telescope has revealed that the cosmic dawn was not a quiet, gradual awakening. It was a violent, hyper-accelerated chemical explosion. Stars were not just forming slowly in isolated pockets. They were igniting en masse, processing elements at a speed that defies our understanding of stellar physics, and organizing themselves into massive, structurally complex galaxies almost overnight. If we look at this through the lens of a linear universe, we are forced to invent absurdly efficient star formation mechanisms that have never been observed anywhere in the modern cosmos. We have to assume that the early universe possessed a unique ability to convert gas into stars at nearly 100% efficiency, without any of the radiative feedback that normally slows down star formation in modern molecular clouds. We have to assume that the laws of physics themselves were somehow dialed differently during the first few 100 million years of time. But if we look through the lens of Penrose's cyclical model, the explanation is elegant. The early universe was already highly structured and intensely energetic because it was built upon the active, energetic debris of a previous existence. The intense concentrations of energy originating from the Hawking points would act as localized, cosmic pressure cookers. Instead of pristine gas slowly wandering through an empty void, the gas in the early eon was subjected to immense pre-existing gravitational and thermal gradients. This intense environment would violently trigger the immediate, widespread collapse of gas clouds, fueling hyper-efficient star formation and forcing generations of stars to live, die, and enrich their galaxies with heavy elements at a speed that seems impossible within a linear timeline. The early universe looks mature because it was born out of maturity. This paradigm shift also breathes new life into the study of the oldest structures we can physically observe. Consider the massive protocluster discovered in late 2024, sitting at a redshift that places it a mere 650 million years after the starting gun of creation. In a standard bottom-up universe, this structure is a profound paradox. To build a protocluster containing dozens of galaxies interacting within a single massive dark matter halo, gravity must propagate across vast distances, drawing independent systems together over immense spans of time. There is simply not enough time in a 650 million-year-old universe for this large-scale migration to occur. It violates the causal speed limits of gravitational interaction within an expanding space. In a cyclical universe, however, this top-down assembly is a fundamental feature of reality. The grandest nodes of the cosmic web, the intersection points where matter, galaxies, and supermassive black holes clustered over trillions of years in the previous eon, leave an indelible, large-scale gravitational imprint on the conformal boundary. When the new eon begins and the primal plasma cools, matter does not accumulate randomly at the small scale and slowly drift together. Instead, it falls directly into these pre-existing macro-scale structural troughs. The universe forms from the top down and the bottom up simultaneously. The skyscraper-scale structure of the protocluster is assembled concurrently with the individual stellar systems inside it because the architectural framework was already written into the geometry of spacetime before this eon even began. The implications of this transition stretch far beyond the realm of abstract mathematics. They strike at the heart of our place in the cosmic timeline. For centuries, humanity has wrestled with the terrifying concept of an absolute beginning, a moment where something came from nothing, creating a harsh, linear reality that is marching toward an ultimate, cold, dead end known as the Big Freeze. In this standard linear narrative, our universe is a temporary, tragic spark in an infinite, eternal void. We are a cosmic accident, born from a singularity we cannot explain, moving toward a heat death that renders all structure, information, and life entirely meaningless. But Webb's paradoxes offer an escape hatch from this existential dread. By revealing a cosmos that refuses to fit into a neat, linear box, the telescope is validating a mathematical framework where death is not the end, but the ultimate catalyst for rebirth. In Penrose's Conformal Cyclic Cosmology, the very process that was thought to destroy the universe, the infinite expansion, the cooling of all matter, the absolute emptiness, is the exact physical state required to trigger the birth of a new world. The final, lonely evaporation of the last supermassive black hole is not the dying gasp of a failed reality. It is the ultimate deposit of energy that will seed the galaxies, birth the stars, and forge the chemical foundations of the next eon. We are witnessing the opening chapters of a true scientific revolution. Just as Copernicus shattered the geocentric model by moving the Earth from the center of the solar system, and just as Hubble shattered our isolated worldview by proving that the Milky Way was merely one galaxy among billions, the James Webb Space Telescope is shattering the illusion of a single, linear timeline. The universe-breaking galaxies, the impossible black holes, the ancient chemical signatures, and the undeniable rift of the Hubble tension are the structural echoes of an eternity we are only just beginning to comprehend. The Big Bang was not the birth of time, but a magnificent, fiery bridge between eons, a horizon where the closing notes of a forgotten universe harmonized perfectly to strike the opening chord of our own. This is perhaps the deepest significance of instruments like the James Webb Space Telescope. Not in their mechanical precision, not in their ability to collect photons from billions of light years away, but in what they represent about human potential. about our capacity to extend our senses beyond the limitations of unaided perception, about our ability to translate the language of the cosmos into understanding. What will you answer?